Hello, hello. Welcome to the stream. Seems like my dashboard's not quite working. I will be able to see comments in a second. Let me know if you're having any issues with audio or video. But I am very excited for today for those that have been following along this whole journey. We have been building this incredible UPS prototype. We've been working on the power input, a couple buck converters, isolated flyback converter, and today we're working on this bar down here, which contains it's a 5 kilovolt isolated amplifier that we're going to be using for feedback on the inverter output. So this end will be connected to the mains output, and then this will be connected to the controller, but we need some isolation in there. Similarly, this isolated current monitor, we're going to be testing that out. It can handle up to 20 amps. We're not going to be able to push it quite that hard today, but we'll push it as hard as we can with the lab power supply. Yeah. But for those that have been following along, you might know that isolated voltage and current feedback is not what we were planning on talking about today. We were planning on talking about, by the way, coffee. We were planning on talking about, what was it, the battery charger? Yeah, we were going to be talking about the battery charger, but as you notice, the battery charger is not assembled, and all this other stuff is assembled. So I did indeed build the circuit just like I promised. I built the circuit just like I promised, but we ran into a little bit of a problem. So before we really dive in, what I want to do is I want to tell you the story of how we got here. And I'll make it the short version. Since a lot of the folks, a lot of our regulars aren't here yet, but still want to just kind of run through it so that in the archive and all that you can see it from start to finish. So basically what happened is all of these circuits rely on having 5 volts, 12 volts, and 15 volts. And we've really tried to get these converters to work well. And these are using the like the NCP 3020 from On Semiconductor. And I have just been convinced that there is something wrong with this controller. Like, the part says that it's rated for operation up to like 40 volts. We're using it at 24 volts, and the low side gate driver just nerfs itself over and over and over and over again. And I've dug into the numbers, and I don't have a reasonable explanation for why it should be doing that. And to be honest, I'm sick of blowing up controllers. It's to the point where at first there was a save operating area issue, mitigated that. There's no more issue like that, and just like sometimes on power up, the gate driver will just destroy itself. And so it was like, as I was doing this progressive optimization, I had this to a point where all 3 of these converters would go into a hiccup over current recovery mode at around 3 amp load. Nothing would overheat. It would actually work quite well. Then I walked away, came back, plugged it in, powered it on, and 2 of the converters blew up. And I was like, what? I was tuning this morning, and I just came back, and now they don't work? Like, that is completely unacceptable. I need this thing to be consistent. I want consistent, good performance. That is what we are going for. And if this NCP 3020 is not going to deliver, I want no part of it. So we're moving to a different controller, a different power supply design. And I did this with a couple goals. We'll talk about it more in a couple weeks, but I was looking at this design. I'm like, that is a lot of parts. We're gonna have to pay for assembly. It's gonna be pretty expensive for assembly. some of these caps, the input and output caps, are only rated for 25 volts. That's not great. Really, we should bump that up a little bit. So designed out a couple of these massive parts, put on a couple more MLCCs, upped the switching frequency, which reduced the amount of capacitance required, and all sorts of these good things. Kept the power output the same, so we're still doing the 5 amp output. 4.5 is really what it's designed for. You need about 3, but so we got plenty of margin in the output current. And I've reduced the part count considerably since we're using a controller with an integrated high side FET. So basically we cut the part count in like a third, shrunk the footprint of the design by about 33%, and yeah, it should be excellent moving forward. But we don't have those prototypes in, and the converters are still in various states of disarray, and we are once again out of controllers and out of FETs. So I couldn't build the battery charger because we're out of parts for the battery charger. So, and thanks for joining the stream. Thanks for joining the stream. So what we don't have is a battery charger because, like I just explained, we're moving away from the NCP 3020 and in fact are sick of it blowing up. But what we do have is a lot of really fun circuits to test. Like, we've got these precision analog references. We've got some temperature sensors that I want to debug from the old UPS. We've got our 3v3 generator and power on reset circuit, where this is simulating the master controller resetting a daughter card. We've got the isolated feedback amp and the isolated current amp, and we're just gonna go nuts. So fingers crossed. Power on. Hey look, 5 volts still works. First thing I want to talk through is, well, let's see, where should we start? I'm kind of feeling the temperature feedback. So on the old UPS, the Gen 1 UPS, this circuit seems to have worked, but I observed a very inaccurate, it just didn't seem to be working right. Like, we would measure 2 analog temp sensors, and they would read drastically different values, like 10 degrees off, which is weird because these are supposed to be like 1% tolerance, 2% tolerance, they're supposed to be pretty accurate. So I was like, what the heck is going on? But since it was kind of nestled in there with high voltage, I never got a chance to debug it the way that I would like. So what I have here is I have one of our controllers from the from the phase 1 UPS. I've broken out the analog reference pin and 2 pins that are supposed to be hooked up to those temperature sensors. So what we'll do is we'll wire this all in and see if something like the ADC sampling the signal is causing some distortion. Hi Dave. Welcome, welcome. Happy to have you on the stream. So as a first pass, what I'm going to do is I'm going to measure with the multimeter the voltages present on the references and the temp sensors, and we're going to make sure that those are all within spec, because if these aren't reading right, nothing will work. So here's datasheet for the reference, and here is datasheet for the thermistor. So in here it's saying we should be accuracy of plus or minus 1 degree, and we should be 0.1%. Alright, so 0.1% of our 4.096. So that should be within, oh my goodness, is that 0.4 millivolts? Or is that 4 millivolts? Within 4 millivolts. Alright. So we should be in the range of 4.092 to 4.1. Alright, let's see where we are. Oop. Yes. Whoa. Why am I in the millivolts range? Alright, so 4.089. I trust this meter. I don't know if I trust this meter that much. That's pretty close. I have not counted this in years. So I don't know if that's pretty close. So you should be a couple millivolts above that. Let's see if this one's, oh, this one's about the same. This one's also reading a little low. Could be the meter. I'm usually not looking at, 3 positions below the decimal point. I'm not usually too concerned with the 4th digit. And honestly, this isn't a super precision meter, so that might actually be within spec for this meter. Yeah, I'll call that close enough. The big thing I want to check on top of that is what these temp sensors are reading. So we're reading 0.748 volts on one, and then an adjacent temperature sensor, 749. Alright, so those are, wow, they're very, very close. So even if our micro is reading those voltages incorrectly, I would expect them to be the same. Alright, now we know. I need to get ground tied over. Maybe we'll power cycle for this one. Let's shut her down. Okay. Get the scope fired up. I have a feeling I'm gonna want to look at these waveforms. Got power for the micro. We'll get this all wired in. Yeah, looks like we got a couple more folks joining. Welcome to the stream. Happy to have you. Let me know if you guys have any questions. Cool. So analog temp sensor, the first, getting that wired in. Analog temp sensor, the second, getting that wired in. I got ground hooked over. We just need our analog reference. So I had to tweak the firmware on this guy just to set up the ADC for the 4.096 volt reference, but that should all be good. So I'm gonna connect our 4.096 reference over to the VREF pin. Hopefully we'll be able to power this thing on, and everything will look hunky-dory. Boot it up. Alright, we have data. Hopefully you can read that. I'll zoom in just a touch. Yeah, it seems very legible. If I could get the thing in frame. There it is. Sweet. So, need to go over to the other menu. There we go. 299 degrees C, huh? Really? That seems a little high. Hi, JD. We are currently looking at the analog voltage references. Here, I've got the schematic here as well. Let me grab this and show you. Alright, so on the front page of the schematic, we're looking at the 2 analog voltage references, and we are looking at the temperature monitoring right next to it. Those are the two circuits that we're testing. That is pretty weird that we're getting 294 degrees C. I'm no expert. That seems wrong. Okay, let's take a look at these voltages. Let's take a look at what we are seeing. Oh, 7.5. Those are slightly different. 751. Analog reference 4.09. So it seems like this is all going okay. Let's try resetting this thing. See if we can get it to power on and measure it better. Really? 290? What in the world? Oh, wait a minute. It's now the charger. -1? What? Inverter -1? Why? So that must just be a floating pin. They're out of range. That's bizarre. Well, I guess we'll just have to decode it manually, but at least we know it's being sampled. What I wanted to do was hook up the scope to these references. By the way, welcome, JD. I might have forgotten to say that, but welcome. Happy to have you. So if we switch over to the webcam. Oh, yes! Look at that. You guys can see the scope so well. Yeah, got a new camera for that zoom in. We're away from the basic webcam, and we've got something that I can do fixed focus, manual focus, fixed zoom. So, yeah, I think that is a lot more legible. Hopefully, you guys agree. So what I'm going to do is I'm going to take... Oh, I've got a picture-in-picture view. Let's do that. So what I'm going to do is I'm going to connect the scope over to our analog reference in AC couple mode, and I'm going to look at the ripple that we're injecting on that analog reference by running the ADC. Wow, that's more than one would like. Let's see if I can trigger on that. So we're on channel 2. Yeah, we'll just go ahead and turn channel 1 off. Force trigger. Come on now. There we are. Hey, No Corp. Not sure what the prices are for Cal in the US. 200 for 5-digit meter. Woo! No, it's not an order of magnitude out. I'm like a couple millivolts out. Yeah, 30 degrees C sounds better. So 30 degrees or 0 degrees C output is 500 millivolts. We are measuring about, what is it, 754.754. So if we do 0.754 minus 0.5, we're getting 0.254 millivolts. And where is it? On the data sheet, we are getting, what is it, 100 millivolts? No, 10 millivolts per degree C? Yeah, we're at 10 millivolts per degree C. So it says that we are at 25 degrees C. What is that in Fahrenheit? I think that's about room temp. I think that's pretty good. It's like the analog coming out, the multimeter, if I decode it manually, comes out okay. But it's the micro is currently throwing an error on it. It's giving me a -1, which I think it's just a bounding thing. If I read less than 1C, so when I reconfigured the ADC, I must have hosed something up. Yeah, so we're at 25.4 degrees C. And they are reading the same, which is good that they're agreeing. They're both saying -1, but yeah, like if I let these pins float, it, decodes this. Something else. Anyways, what was I? Right, I was looking at ripple. Ripple on this guy. Force trigger. Why is this not wanting to trigger? Oh, because we're still on channel 1. There we go. Run. That is weird. Oh, I'm not grounded. It's like, that looks like 60 hertz. Yup. It's because it's 60 hertz. We're on the ground mat, which can lead to a little bit of that. Hey, look at that. So much better. Alright, but I think we're still seeing some noise in there. Oh. What kind of magnitude are we looking at on there? Yeah, I'm not too concerned with the hardware. I saw your cool. Yeah, I think the hardware is doing okay, but the cool thing about having this platform is it'll let me debug that interface between hardware and software. Yeah, I'll zoom in on that for you. The trigger's not perfect, but you get the idea. So we're seeing, oh my goodness, that's a lot of ripple. 100. What are we at on the delta? 78 millivolts? Really? Wow. Wow. Wow, that's a lot. That is a lot of ripple on this analog reference. Alright, I am going to hold the micro and reset. I would expect that to stop the analog referencey stuff. Whoa, that ripple is existing all the time. I'm no expert, but that seems like a lot of ripple for like a precision reference, which makes me think I've added bulk on the output, and perhaps that is making this thing become unstable, even though I added a series resistance. So maybe we should try removing C32, because yeah, 78 millivolts of ripple. That's a lot for a 4.096 reference. That is a lot. But what I'm doing is I'm checking to see if that's within spec. So here we've got the yup. Almost 2% ripple. Yikes. Output noise. Yeah. I think we should replace that. I think we got a 2.2 mic. Maybe we'll try putting on a 0.01 mic. I saw somewhere 100 puff in this datasheet. It called out characterizing it at 100 puff. Maybe we'll do that. Before we do, let's check out the 3-volt reference. Same deal. Lots o' ripple. Let's check out our temperature sensors. Those are looking nice and clean. Oh, sorry. There we go. So that's what our temp sensor output's looking like, AC coupled. Very clean. No real concerns there, and that's with the ADC running. So, and if there was going to be lots of noise here, we would see it. And that just looks like the scope being at its limit. This isn't like a top of the line scope or anything, you know? This is, we're kind of pushing the limits of what this thing can measure. So I think we're doing just fine. Morning, WTP Gaming. Welcome. Welcome, welcome. For those chopping in, or for those that didn't see the first couple of minutes, we were supposed to be doing the battery charger today, but we're doing the sensitive analog stuff and the interface to our future micros, because you might notice this buck is blown up, and the controller, basically I was working on this offline. I was tuning these to get the hiccup current protection working, and I had them all tripping at 3 amps where it would just kind of cut back and do the hiccup recovery mode and all that. It was great, and then I turned it off, walked away, came back, turned it on, and it all blew up. And I was like, nope, this is the last straw. I am not dealing with this anymore. And so we're building some, or actually built, they're shipping right now, just a little dev board for a new controller that we can hot wire in here, pick up the fuse, and it should be a ball of fun. So we'll be using those new bucks in the coming weeks. Did get this tuned though. If I had 12 volts, I could show you how great it is, but we don't at the moment. So we'll have to save that joy for next week. But it should be ready to go for next week. We should get that all fixed up. Nonetheless, we've got a lot to test today. Yeah, so I think I'll flick on our solder station, and we will replace the caps on our analog references with what was it, 0.01 mic. Give that a try and see how that looks. So that could be a thing, because we pretty much pulled the same circuit forward from the previous UPS. So if we were having issues with 100 millivolts of ripple on our ADC reference, that would be bad. The result of that calculation would be very different. Yeah, maybe, I don't know, should I try no capacitance first? Maybe I'll do one of them with no capacitance and one of them with just a little bit. One cap removed. Oh, no. Oh boy. Oh boy. Now I've done it. I am soldering left-handed for what it's worth. Well, that was right-handed. Oh my goodness. What am I even saying? Where am I? What are those? I don't know. Okay. I'll quit messing around. 4.096. 0.01 mic. 0.01 mic. Man, we do not have a ton of those. That's alright. Much less capacitance. I think we had a 2.2 microfarad cap on that, which is approximately way too much, right? So that's probably related. Those are internally buffered. They've got an op amp in there, and if you put too much capacitance on the output of an op amp, you can make it ring. You can make it marginally stable or unstable. Oh, I was just gonna put this on 1. So I wanted to add capacitance, so when our ADC goes to take a little gulp of current, the ADC says, oh, I want to measure something. It's pulling energy from this reference. I want to make sure it's got enough capacitance there that like the op amp can keep up, so it'll source a little transient gulp of energy and the op amp will get there eventually. But if there's ripple only when we're sampling the ADC, that'll be all the time and it could impact the accuracy of our measurements. That was the intent of adding capacitance. I believe I just added way too much. Something like this, you really don't need a lot of capacitance. Alright, I think there's enough on there. I think that's connected. Let's power her back on, see how she looks. Let's see if some of that ripple went away. I gotta get the ground connected here. Hey, that looks way better. That looks excellent. What is that random noise? Are we zoomed in more? That is still not great. What is that? There's nothing sampling this 80. Oh, you can't see that. Dang it. I just gotta do picture in picture all the time. See, this is what I'm seeing now. I'm seeing this like periodic nonsense. I'm seeing periodic nonsense. I don't like that. I'm gonna take the multimeter, get that in frame, maybe, yes. Alright, yeah, so we're gonna measure the voltage present at this reference. See what that looks like. Maybe we're up closer to 4.096. Hey! Oh, come on! You saw it for a moment. You saw the 4.096. It was there and then it was gone. Why? Okay. That's interesting. Let's check out the 3-volt one, the one with no capacitance on the output. So that looks about the same. Interesting. So in removing the excessive bulk, we're seeing this periodic weirdness. I almost want to look at that DC coupled. I think I might want to look at that DC coupled. Just to see. Huh. Visible. Super visible. Interesting. Making multi-phase buck? I love multi-phase bucks. Yeah. Depending on what you're doing, as power gets higher, multi-phase converters, they are pretty sweet. I mean, we could definitely make one. It's really just, you take the buck we've already made, and then you add like a synchronization controller to them. Like you can just get 4-phase, 6-phase clock generators from Analog Devices. I think they got one for like $4 or $5. You just take that thing, you feed it into the sync pin of a bunch of otherwise normal buck converters, and now you got multiple phases. The analysis is a little different, but overall the ripple current's less. Yeah. So we definitely could. Definitely could. For this load level, like 5 amps, there is absolutely no need, but if I was pushing like 100 amps, 200 amps, and I really wanted to, yeah, it's like a lot of computer peripherals, they'll do that. They'll use multi-phase. Man, that bothers me. Sorry, not the multi-phase buck. This is bothering me. The solder station's going to sleep. Don't mind the beeping. Everything's fine. Yeah. So we're measuring 3.02 volts on the scope, which is shockingly accurate. I can't believe, because scopes are not made for measuring DC. They are not very accurate for measuring DC at all. And yet, it's within a couple millivolts. I've seen worse. Yeah, that is weird that, like... Don't know how I feel about that. I really, really, really don't know how I feel about that. Pick up from the alligator lead. There's no alligator lead on these, and I can unplug the alligator leads. Could be. I'll just get it all off the board. All of it, because it could be coupling through. Well, this seems to be significantly reduced magnitude on the one with a little bit of output capacitance. I wonder if that's a function of too little. Because now we're seeing a little more noise. Over there we're seeing barely any. So it could have been a function of alligator lead. Oh, you know what? I think you're right. Good call. Good call. Japan getting hammered by typhoon. Feedback pin. Did you set up a filter? Yes. Wait, feedback pin? There's no feedback pin on these analog references. It's wired internally. Interesting. Alright, here's what I'm gonna try. I'm gonna try going, so that was a 0.01 mic. I'm gonna try 100 pico, or 1000 pico on the 3 volt reference. See how that looks. It could also be, oh, if you were saying this alligator lead from the ground, could be that too. Sorry, I got distracted. You asked a question about output filter. I added a little filter on the output of the references themselves. It's a 5 ohm series element with a capacitor of currently being tweaked size. I believe the datasheet called out 1000 puff as the capacitive load that they used when characterizing it, but in my mind that wasn't saying add a capacitor, that was saying we're adding a little bit of capacitance here to deal with the fact that this is going to be hooked up to a micro and there's going to be some parasitic capacitance. That's what I interpreted it as, but I don't know. So I'm going to test 1000 puff and 1 order of magnitude above that. We're going to see which one of these looks better. Technical term. We're using the SC75 version that has 3 ground pins. We're using, what am I doing messing around? Hey, look, a data sheet. We're using, oh no, yeah, we're using the SAT23. Ground. Yep. Anyways, alright, power back on. So, okay, so now we're seeing that crazy noise again that was kind of gone before on the 4.096. Maybe these need to warm up or something. Could this be from the buck? Could this be from the power input? This could be from the power input. I'd believe it if this NCP 3020 was in some kind of discontinuous terrible mode. Let's see. Let's see if I probe the 5 volt rail. Oh, well, there's your answer. It's coupling in from the power supply. Our power supply is nasty, dirty, terrible, other derogatory words. Yeah, it's common mode coupling from the 5-volt supply. So, yes. There we go. That would be where it's coming from. Yeah. Laughing at me? I call this preparation. Having the datasheet on hand. So what I'm going to do is I'm going to add a little bit of load to that 5-volt rail and see if we can get this thing into a continuous conduction mode, and then maybe these start acting a little better. Still, we definitely had too much capacitance. I was definitely making the reference a little unstable. That was my bad. I will strive to not do that in the future. We're probably going to use either the 100 puff or the 1000 puff for the 0.01 mic, depending on how I'm feeling. Alright, so we got this, need a ground clip anywhere, sure. Use the same one. And we'll grab 5 volts off. Add a little bit of load. Yeah. Well, add that to the list of reasons why I don't like this controller. We added a load, and it just doesn't care. Maybe it's not enough. Yeah. I don't know, our 5-volt rails just got that nonsense on it. Well, that'll be something to keep an eye out for as we move towards the new buck design. I have a feeling a lot of this weirdness is going to go away. What I started to notice the more I was looking into alternate controllers is that when you want an advanced feature, like, for example, synchronous rectification on a buck, but you also want the cheapest controller money can buy, you run into this little bit of conflicting requirements kind of messing around where the cheapest controllers are not necessarily the best. And their implementations of synchronous gate drive are not the best. You need to pay for the best. And so for better or worse, I ended up moving towards a cheap controller, like approximately the same cost, but I'm using diode rectification instead of synchronous, which doesn't feel as good, but it's sufficient for our requirements. So it's kind of hard, but I really think it's the right move, because we can get a controller that will be more robust for what it's doing because it's not doing as much. Does that make sense? You guys pick up what I'm putting down? You feeling that? Hopefully. Hopefully, forgive me. I like synchronous rectification just as much as everyone else, but it just doesn't really make sense for what I'm trying to do. If it's synchronous rectification at the cost of your power supply blowing up intermittently, that doesn't seem like a good trade-off. That doesn't seem like a good compromise. Yeah. Yeah. Well, I started looking into controllers that would give us good synchronous rectification. Like, I don't know how this didn't just jump out at me, but they don't tell you how they implement it. Like, a lot of controllers say, we're using diode emulation, or we have guaranteed dead time through this mechanism, something along those lines. They just didn't. Which makes it really hard to design a gate drive network to, like, make sure you're not hosing up their synchronous rectification strategy when you don't know what they're doing, and they're just like, don't worry about it. I'm not about that. I'm not about that life. Alright. Let's hook this up. Hey! Holy crap! Guys, look at this! So I fixed the wild oscillation, and it works now. Our reference works. Can I zoom in? Not out. In. Yes. So it's still jumping around like a crazy person, but at least it's in the ballpark. Turns out 100 millivolts of ripple on your analog reference, that's a problem. Nice. Nice. So yeah, that was the problem. Mitigated. I notice on the scope though, now that we have this thing running, sorry, that's the microscope. Now that we're actually sampling the ADC, a lot of that noise came back. But at least now it's noise that's like reasonable. Yep. So now if I go to picture-in-picture, you guys can see our two temperature sensors. They are kind of trending around each other, but there's definitely some noise happening that is not super. They rarely read the same value, but if I just go ahead and take the DMM, I'm going to measure across the two temperature sensors. So this will give us the differential voltage measurement between the two temp sensors. It'll tell us like the whole stack up of error. I'm getting 1 millivolt. I'm actually going to switch this into the millivolt range. 1.2 millivolts. All right. So basically, no matter what temperature our display is reading, I would expect these two temperature sensors to read the same number. One of my probes slipped. Right? We're reading less than a millivolt difference. It's 10 millivolts per degree C. So if one says 23, the other one should say 23. If one says 21, the other one should say 21. Why? Why are we seeing this error? That. Sorry, was that too much? Okay. So I'm guessing that's our sample rate. And I'm going to do something. I'm going to see if more capacitance helps. Hard to say. I'm using myself as a capacitor. I'm touching the net, adding a couple more puff. Man, that's hard to say. It could also be our ADC settings. Maybe I'm using like a super fast mode and I need to slow it down a little bit to make the thing more accurate. This is what I was observing on the old UPS. It didn't make me feel too great. I would prefer for that to be a little more constant, since I think it should be. I don't know. What do you guys think? JD, let's try it. Was that the more capacitance? I can just plop a little more on there. So that was the 0.1? 0.01? I don't even know what I should do. I don't know whether I should go up or down. Here's what I'll do first. Before we do that, I want to probe the other side, right? I added a 5 ohm resistor and a capacitor. But I want to see if that ripple is propagating to the other side of that network. Maybe I did more harm than good. Nope, looks exactly the same on the other side, which makes sense. I wouldn't expect a whole lot of current to be flowing. That is interesting. Let's measure that with the cursors. Yeah, I have an RC filter on the output. Right now it's a 5 ohm and a 0.01 mic. That's what we got right now. Come on now. And what I just probed was both sides of that RC filter to see if the filter itself was adding a significant, or having a significant effect. And what I'm seeing on the filter side is, what is that, 150 millivolts of ripple. Oh, wait, what? What I'm seeing on the other side is like no ripple at all. Okay. Yeah, I made it. I don't know. Right now I'm feeling R lower. So I'm probing the actual analog reference output side. And it looks a lot better than this side. Oh wait, what? Was I just... What in the world? I think my probe was just not quite on it. I think I was just like over the ground plane. Yeah, okay, so we're seeing it on both sides of that filter. Oh. We could try R higher. The higher that resistor gets, the more we're going to be relying on the output capacitance to maintain a stable... Yeah, if I pulled the resistor higher, I could leave that massive capacitor on here without affecting stability. Maybe that's what I should go for. Let's try that. Let's see if I can't get this thing to be stable with our massive capacitor by adding like a 1K or I don't know, something like that. What are you feeling? I'm feeling a 5.11 kilo ohm resistor. I've been a really big fan of that value. Just the 5.11. Yeah. Yeah. 'Cause it'll give it a nice bucket of energy to pull from when it needs to do a sample. I like the way you think, No Corp. I like the way you think. Yeah. Yeah, right? I agree. Seeing a difference is definitely ideal. It means it's doing something. Ugh. Yeah. Let's do it. Prototypes are fun, am I right? This is like... Man, this will impact the accuracy of the inverter output. This will impact the accuracy of our temperature monitoring. This will impact everything. This is so important. And I'm really glad I'm not debugging it. Cool. Thanks, JD. I'm glad you're enjoying it. It's just like, man, we're just messing around. You know? That's my favorite part about this. My favorite part about this whole thing is we're just hanging out. Super laid back. So, not to pry No Corp, but you're full of good ideas. I'm getting the impression that you are either a practicing engineer or were and are retired. Curious if you're willing to share. I'm curious, because it's like whenever you sound something off in the comments, man, it is, you can just kind of tell that it's seasoned with experience. So just curious. Alright. We got our 2.2 mic cap back on. What do you guys think? Oh, works better when you get the solder out of the way. Okay, so we've got our DC monitor there. Where's my top hat? Here it is. Top hat engaged. Analog reference being probed. Yeah. Yeah, JD. I'm glad that you're enjoying it. If there's anything in particular that you're like, man, this is sweet, definitely let me know. I'm open to feedback. And like, yeah, is it just like the knowledge sharing, watching the debugging process? Is that what you're into right now? Is that what's cool? Hey, now that looks pretty solid. The ripple on that reference. Whew. Yeah. Yup. That, yes. Okay. We have crushed this. Ant, meet sledgehammer. That analog reference is perfect. Yeah. There is not very much ripple on that at all. So yeah, we'll keep the 5.11K, 2.2 mic. Mr. Aviation, I'm very new to electronics, like very new, and have no idea what you're talking about. Dude, welcome. I am so glad that you're here, and I think the fact that you're here just trying to learn is awesome. I hope that, even if you're at a stage where you're just like, what is electronics? Yeah, RMS, root mean squared. I think he's seeing this little note down here. So I'm having the scope calculate a couple things. You can have this take some measurements for you. So like, if I was looking at a sine wave, the best way to think about that is DC equivalent, right? We're gonna pull out the wave gen. We're gonna pull out the signal generator in a little bit, and we're gonna be testing this with an AC measured waveform. So hang around if you can, and we can use that RMS, and I can show you how it's DC equivalent of an AC waveform. But that's the fundamental of it. It's like you get an equivalent amount of power. So for like a mains waveform, you get 120 volts or 240, depending on where you are. That's RMS. You just might not always say it. So if you had 120 or 240 volts DC, apply that across a resistor, you get the same amount of power as you would from 240 AC, but the peak waveform is square root of 2 higher. So multiply that by 1.414, and that's your peak voltage. So that's real high level. But seriously, dude, Mr. Aviation, I'm so glad you're here. So glad that you're learning. Whether you be in like the Arduino prototyping stage or in just learning about resistors and capacitors, man, we got some component fundamentals. Check that out. Definitely want to encourage you to keep pursuing this knowledge. For now, I'm pumped that this worked. So we're going to change both of those to be the 5.11K with the 2.2 microfarad bulk, and that will be the design moving forward. Where's my pen? Really? Where's the guy's pen? You guys got a pen I can borrow? It was right here. Well, whatever. Steady as a rock. Absolutely. Absolutely. Doesn't get any better than that. And that's with the ADC sampling and running. Like, that is awesome. In fact, maybe I should change the temperature sensors. The temperature sensors seem to be doing okay with the smaller bulk. But, here's the pen. Here's the pen. I think we can safely move on from the analog references. I think we're good. So I'm just gonna redline this. Well, I guess it's a black line, whatever. We're gonna say 5K11 plus 2.2 mic. That's where we ended up. And on the temp sensors, I might bump those up to a 1 mic. Yeah. Well, we should probably proto that before I just go making changes. Let's do a 1K. 1K plus 1 mic on the temp sensor. Let's make sure that doesn't hose it up. Same somewhere in the applied electronics space as a profession. Okay, works. Yeah. Cap rated at 240 volts. No, that would not. I like that. So that was a tip of the hat. Hey, you say you weren't too familiar with the field. So there's like low voltage, which is, I think it's anything below like 500 or something. That range goes pretty high. What's still considered low voltage? Yeah. Alright, so we got a 5K11. We're gonna need our 1K. Yeah. Yeah, I mean, electronics as a hobby is one of the coolest things. In my opinion, it's just kind of like there's a problem and you're trying to solve it. Whether it be you want to have cool LEDs in your house or you want to build a UPS, man. Like, you just go for it. I think that's so cool. Low voltage is 120 to 1500 or 50, 2000. Hey, I was pretty close. I don't remember exactly what I said, but I was at least rough order of magnitude. I'll take that. There we go. Got the other reference soldered in. We're going to tweak these temp sensors to 1K filter resistors. Play with a microphone. Oh boy, that sounds like a party. That sounds like a lot of fun. You want to use it to make like a Jacob's ladder or something? That's a pretty fun project. So first of all, I got to be a dad for a moment. So high voltage is dangerous. High voltage AC is slightly less dangerous, but it can kill you. Don't hurt yourself, please. I much prefer you alive. Yeah. So definitely be safe. If you feel like something is sketchy, it probably is, and maybe you should rethink your strategy. I think if you treat high voltage with respect, there's a way that you can do whatever you want to do without injuring yourself, but depending on the voltage and the power and whatnot, you might need to be more or less careful to make sure you're being safe. For discharging, I saw JD, I think he said just use a resistor. Absolutely, resistor will get you there. Dead shorts are a little more exciting, which is usually not a good thing. But yeah, just make sure that it's not discharging through you. You should be all right. What do you have on breadboard? Yes. What do I have on the breadboard? Great question, Big Adam. Also, welcome. I think that was the first shout out. What we've got on here is a PSOC 5 dev kit from Texas. No, from Cyprus. Cyprus PSOC. I can't remember the name of the kit, but I've got another one over there. Oh, it's the CY8C kit-059. I think they've actually got these on Amazon for like $15-20. I can drop a link. I can drop an affiliate link after the stream. It's a really fun series of micros. For anyone who's played around with micros before, this is just a logic translator that's not doing anything, and a button. But it's really just this. I'm using this because this is the micro that we used on our previous version of the UPS. So I've got some firmware written that is made to interface with a very similar implementation, but slightly different. And we're looking for a 1 microfarad cap. Here she is. But yeah, the PSOC 5 series, they've got native USB support. They've got SAR ADC and a more traditional ADC. They've got all kinds of digital and analog interfaces, and they're configured like a little mini FPGA, so you can actually write your own HDL, you can write your own Verilog or VHDL, and make custom hardware components in there. So if you want to implement a custom communication protocol, you can do it in hardware, which is so cool. As long as it's not too big. As long as it's not too big. Yeah, definitely. Yep. One must treat high voltage with respect. I know everyone's got their own style. I don't know. I don't want to say anything bad. But I'll just say that perhaps the way that Electroboom handles high voltage does not encourage best practices. Perhaps. Or maybe it's demonstrating what happens if you don't follow best practices. But either way, I generally try to be a little more careful than that. Okay, powered back on. Gotta hook the ground clip on. Woo, those are nice and clean. One of those is hooked up to our analog temp sensor. The other one is hooked up to our 4.096 reference. Now that's just not even fair. Let's try a reboot. Come on now. What? What now? Why are you so mad? Bizarre. Oh, wait a minute. That's why I didn't actually hook them up. I was like, these look so clean. Why is it not reading? Can you explain transistor bootstrapping? Probably. I've come to realize that I understand things, but I don't always understand them in the word that other people use. But I'm sure that the concept of transistor bootstrapping is nothing that isn't constrained by physics. So I'm sure that I can explain it. I just don't know exactly what you're talking about. Ah, okay, got one from DigiKey. Resistor or oh, you got a Jacob's ladder from DigiKey? What? That's so cool. No corp yes, as in amplifiers or for power conversion gate drive. That was an or, and then yes. Now, I feel like that's a quick Google search that I gotta do. All right, sweet. So just confirmed that the temperature sensors are working better. The analog reference is great. Time to move on up. All right. Analog reference done. Anyone have any more questions about this whole thing before I tear it down and we switch over to the next thing? It's just a question mark. I think that's okay. Cypress PSOC, I think that's okay. I think so. It should look like this. So these are two dev kits that I've used before. This one's for PSOC 4, this one's for PSOC 5. This one is the one that I'm using here that's got the native USB support. This one's a lower power micro. We're actually using this one to drive the old inverter, but we're replacing this with a PSOC 6. So, not sure if this one's getting carried forward or not, but it's a neat little part. So if it looks like this, CY8C Kid 059, that's the one. That's the one. Oh yeah, cool. JD, nice. Yep. Yeah, I got mine from DigiKey too. I think they were a couple bucks cheaper and I was already ordering it from there. The Amazon one is like, if you're not already buying something from DigiKey, it ends up being as cheap or cheaper, and if you've got Prime, you get the 2-day or whatever, so it's a horse apiece, but if you're already buying from DigiKey, definitely get it there since you're already paying for the shipping, so. Alright. I don't see any questions coming on this, so I'm gonna switch gears. Over to the next thing. Alright, so there's something that I think is gonna be polarizing, and I just wanna do it. I just wanna like dive in before we get serious again. I wanna do something a little silly, just to see how you guys react. I wanna see what's gonna happen, alright? This is one of those you're gonna love it or you're gonna hate it sort of things. And let's find out. So this one is a different dev kit. This was something I just threw together real quick using an Arduino, since it was leveraging a library that I knew was readily available. And just gonna wire it into our system here using the 5-volt regulator we have on board. Just gonna wire it into ground, 5 volts, and then we've got a data pin that's going to hook in over yonder. Oh, you have no idea. I don't think Arduino should be polarizing. I think Arduino is great. I think that anything that makes electronics more approachable, anything that makes it easier to get into electronics, it shouldn't be polarizing. It should just be awesome. Right? I'm all for sharing this wonderful hobby with others. Alright. So, got it powered on. The Arduino's going. I'm gonna hook up the scope to dang. Alright. Ground. Scale. I want to show you guys what's going on this data pin. Okay. Scale it. Oh, I'm in the wrong channel. That would be why. And let's do a DC coupling. Alright. Alright, so that's what we got going on. And I might be strategically. Oh, high side gate driver. Oh, bootstrapping. Ah, I understand now. I get it. Yeah, that's super simple. So it's using a diode. Alright, you guys ready to be polarized? Yeah. We added RGB fan support to the UPS. Yeah. I tested. How do you guys feel about RGB? Because we need cooling fans, and I'm like, RGB seems neat. All right. So yeah, that works. That's good. It's good that we can control addressable RGB strips so we can have an RGB UPS, because why not? I know, right? So we can do all kinds of animations, right? It's like any RGB strip. This is just one of the demo programs that comes with it. So we've got fan control that's coming in, and then it's just got a separate RGB header, and you just kind of, yeah. Glad Mr. Aviation. I'm glad you like it. I don't know. Something about it. It just seems so ridiculous, right? We're gonna have this main board with a bunch of fans like next to each other to just blast this thing with cooling, and the thought of them flashing and strobing and being generally awesome. I mean, we could use the color to indicate like temperature of different substrate. Like, we can actually use it for something kind of useful. Is it noise the fan? Not sure what that means. Hey, Tested. Glad you could join. No problem. We're still going for a while. You didn't miss us. Dave thinks it's cool. Yeah. Yep. I'm just using the standard header. Like, if you buy a motherboard, like a computer motherboard, they've all got this header on there. It's just a basic machine pin header, and you can just plug in, and then you plug in your 4-pin fans. We'll have PWM fan control with the funky colors, so it'll be neat. 1 million volts. I think you're gonna struggle to find silicon for that, but hey, anything's possible. Alright, RGB fan works. Good. Wouldn't want the RGB fan to not work, so that's excellent. Alright, we'll move on. We'll move on. Yeah, basically just added a little ferrite bead on the signal line. Just wanted to make sure the ferrite bead wasn't going to mess up the communication. Yep. It's a pretty slow protocol. I wasn't too worried. So I think that's actually all the dev kit debugging that we needed to do. The rest of it should be... Oh, no. Yeah, we got the signal generator, which isn't really a dev kit, but we got the signal generator, we got the power and reset. Got a couple more fun things to do. Let's do the power and reset next. Seems like we need to have RGB, but effectively high side off, low side on. Diode charges cap. I mean, need RGB? We have RGB. Yeah. Should be loud like electrons. That fan's not too loud. Like, I use them in my computer. They're alright, especially because we got PWM control. You can turn them down. Alright. Good idea. Use color LEDs to show temperature. Yeah, you can do all kinds of stuff. Trust me, I just connect to the... I will make it happen. Alright, man. I think this falls well within the you do you territory. Man, I hope that you get up to 1 million volts. Sounds like fun. Alright. So we're doing 1 volt per division. What? How am I measuring negative voltage? This is 3v3. Reference to ground. Why is that negative? That makes no sense. What? I'm sorry, what? Oh, invert is on. Why is invert on? Why would I do that? Alright, anyways. That explains why the serial data looked bizarre. Yeah, there's definitely going to be RGB fan support on this thing, for sure. For sure. All right. So what I'm hoping to capture here is the power on reset pulse. So, right, we've got the button here. When I push the button, we do a reset. I want to catch the falling edge of the reset, which means I need to look at channel 1. All right, and we're gonna do a single shot capture, reset. That looks quite good. It's a really sharp transition. There was no bounce. Looks great. Now let's try to capture the rising edge. And put the horizontal scale in. Run. All right, we're gonna turn off the power supply with our little slide switch. I'll go in single shot mode, and I'm gonna flip the switch as decisively as I can muster. Okay. That POR generator did not appear to generate a reset pulse, unless our scale is, oh, we're in millisecond scale. That would be why it appears that way. So, channel 1 is reset line. Channel 2, blue one, is 3v3. Let's try that again. Let's turn that off. Single shot. Yeah, that seems bizarre. Because it should be generating a reset pulse. Oh, only when the voltage is below a volt, but we rise so fast. The reset pulse would only be in that little corner. Huh. All right. Interesting. Let's see, as long as the source impedances are high, 3 kV is fine. Tesla Jacob's ladder can be fun, although it'd start with... What oscilloscope am I using? I'm using the Rigel DS1054Z. I got it because it's pretty cheap. And it works. I wanted 4 channels, and I didn't need a ton of bandwidth. So, I've had no issues with the scope. Personally, I've used more Agilent, so learning the UI of the Rigel scope has been fun. But I like it. Stop speaking in abbreviation. Abbreviations are for saving paper in books. Abbreviations. Oh man, if I'm using abbreviations, like puff, picofarads. I don't know if I can stop, man. I'll try, JD. I'll try. But it's ingrained in my brain at this point. I will really, really try. Are there any abbreviations that are particularly annoying or offensive, or that you don't always understand? Because I can certainly focus on trying to not use those. But, yeah. Alright, so I'm feeling kinda good about everything on the right hand side. We did the references, temperature monitors, we did the addressable RGB header, POR. Let's check out the 5 volt reset. Alright. Mode, normal, single, boop. What? Trigger level. power down. Let's see what happens to that. Oh my. I see. Alright, let's try that again. There's a bit of a transient there. Yeah, TLA. Mr. Aviation, I saw you retracted that, but I saw it before you did. You're snarky. That's good. Yeah. Picofarads. TLA. Yeah. 3-letter acronym. Beautiful. Beautiful. Alright. So those POR generators, man, I wish I could like see that it's working. There's like a big old transient when I'm turning on the supply, which is making it kind of difficult to capture on the scope. We'll try this one more time. If we don't catch it, we don't catch it. Single shot, capture, go. Hey, that looks like a proper reset. Because 3v3 came up, but we're still asserting the reset line low. Hey, that looks like we're holding it. Hey, this might actually be working. Let's timescale, move to the left. Single. Hit it again. Okay, we shouldn't be holding this thing in reset forever. Are we holding this thing in reset forever? Nope. It does indeed come up. Let's do a force trigger. Yeah. How long are we holding this thing in reset? My goodness. Let's try a single. See you, Dave. Have fun at the pub. No problem. Or do get in a pub fight. Oh, yes. Red, green, blue. RGB stands for red, green, blue. It's just saying that it's a 3-color LED. Yeah. Yep. Yep. Wow, that is held in the reset for a long time. We're at 20 milliseconds per division. What in the world? Why? I just want to capture the reset pulse. Is that too much to ask? Hey, captured the reset pulse. Wow, that is long. Alright, cursors. We'll get this thing measured. Alright, so 5 volts comes up sometime later. What is that? 200 milliseconds, so a quarter of a second. That seems like a perfectly adequate reset pulse. Light emitting diode. Yes. It is indeed a diode, and it does indeed emit light. The interesting thing to me is why our 3-volt reset monitor is not doing the same thing as the 5-volt reset monitor. Because this has given us an awesome reset pulse. But for some reason the 5-volt one's not. I don't know. I don't know what's up with that. So those two are coming up like at the same exact time. I wonder if I load 3v3 to slow down how fast it ramps on. It's almost like we're missing a window. Like, it's turning on so fast that it's just not even acknowledging it as a turn on event. So I've added a little bit of load here. We're going to do a single shot capture, flick it on, still no reset. And give it less impedance, or sorry, yeah, higher current, single shot capture, same deal. Nah, some doesn't sit right. I'll have to double check my circuit, make sure that it's looking right. It's also possible I just cooked the reset chip. Yeah. See, Mr. Aviation, 1 a.m. Oh yeah, we'll do a summary video in a couple days. So you can check it out there for sure. Hope you have a good night though. 1 a.m. sounds like time to sleep. So we've got this fun circuit to test. The isolated amplifier, 5 kV isolated, and I'm actually going to be showing off a little bit of kit that I got a long time ago. If you are a college student, I would highly recommend this. Like, if you had to start somewhere, these are so cool. They're analog discovery boards. They're from Analog Devices. They've got a new version of these out. They're absolutely excellent. And basically what they are is they're a signal generator, a logic analyzer, and an oscilloscope baked into one package. Now obviously, it's not as good. It's not as good as, like, you know, a full-fledged oscilloscope, but it does everything pretty well, you know? Like, it's not great, but it's decent. It's decent. And with that in mind, we're going to be using it to generate a signal here to feed into our ice. Did you guys just see that? The 15 volt rail literally just nerfed itself. This right here, this is why we are changing it. It was just sitting there, being a power supply, no load. The FETs, I guarantee, are fine. The controller was just like, oh, low side gate driver? Nah. Can't believe this thing. Well, I can believe it, but I don't want to. So hooking up the ground reference to the reference on the isolated amplifier. Notice there's a couple jumpers here with these LEDs. I've basically added jumpers so I can short out the isolation and power this thing with one 5 volt rail. Works great. Have you ever tried using MC? Is that a controller? Maybe. I like external FETs. When you use external FETs, you can really make big, beefy, fun power supplies. There comes a power level where you just can't use a low voltage supply anymore, where it just, a highly integrated supply where the power dissipation in the package is just too much. And yeah, so that's when you gotta do something full on. Alright, so now I'm getting the 2 waveform generator channels hooked in. Getting my computer logged in. This does need to be tethered to a computer, so apologies while I get this hooked up. Oh. Maybe it's made for... If it's made for BJTs, I'd definitely recommend using it for what it's designed to use. I would not recommend the NCP 3020, however, unless your input voltage is less than... Oh yeah! Here's the real kicker. So these are rated to operate up at our voltage level, but I go and I look at their dev kit for this controller, and they just arbitrarily limited the input voltage to 18 volts on the dev kit, and I have a feeling there's a reason why. I bet that if I fed this thing with 18 volts instead of 24, it would never blow up. Why the 5 volt has been working? I don't know. I'm just sick of it. I'm sick of looking at that at that data sheet. I'm sure there's a way that we would be able to get it to work, but there's many issues with it, so I'm just scrapping it. Alright, so I'm getting the wave gen set up to make 2 50 hertz sine waves. We're going to make them 180 degrees out of phase. We're going to make 1 volt amplitude sine waves with a 1 volt offset. So peak voltage of, 1.5 volt offset. So we never hit 0. So since these are 180 degrees out of phase, we should be measuring 2 volts peak to peak. I'm going to run both channels, and we'll see what we see. Let's go to the main cam, or sorry, the webcam. Okay. So the blue channel is on the output voltage, and channel 2 is on the raw output, and channel 1 is on a peak follower. That looks like it's clipping pretty hard. Yeah. That looks like something's not quite right. That looks super not great. Uh-huh. So the peak follower appears to be doing its job. It's doing a great job. Low error, like the amplitude. Feels good. We're definitely clipping. Definitely clipping. So I'm gonna see if I pair this amplitude down to like 0.75 volts and make the offset. Whoa, our trigger super not set up right. There we go. That's a beautiful trigger. Okay. So now we're at 750 millivolts with a 1 volt offset. Hey, that's cool. So it looks like the valley of one of those is less, but now that we're not clipping, the amplitude looks correct. That's kind of fun. The peak is really what we're interested in measuring anyways, because I can mathematically deal with that. That is very cool. Actually, we need a third channel. Actually, no we don't. No we don't. So if we pull the scope over and we look at what we're inputting, you can see we're getting a positive and negative sine wave here. And we're effectively full wave rectifying it. And we're doing opposite on the line in neutral. So I'm generating equal and opposite sine waves. See that? So that's a lot. That is almost exactly what our inverter output looks like. Those equal and opposite sine waves. Actually, that's exactly what it looks like. It looks like 2 sine waves opposite each other with a DC offset. We're essentially simulating what this will see by using smaller resistors. Normally you have like 3 meg in series, and in this case we're just doing an amplification factor of 1 by modifying that initial resistor divider. And so what we should always be seeing is, if I feed it the same DC voltage, we should see nothing on the output. We should see absolutely nothing. So let's try that, in fact. Let's make sure that aspect of this is working. Hey! So we're down at the minimum voltage. Interesting that we still get a DC level. I'm sure that we've got some diodes in the circuit. That's probably what we're seeing. Not concerning. Yeah, so we're seeing 200 millivolts. It's our minimum output voltage. Actually, that could just be the output of this op amp. That might be our V out low. Oh, interesting. All right, so what I'm going to do now is I'm going to add a 1 volt sine wave on one side. Whoa, that looks gross. I think we're clipping. We're going to do a 0.8 volt sine wave. Whoa, that still does not look great. Alright, I mean, I'm not here to judge. So I would expect to see 0.8 volts as my peak voltage. Let's take the cursor and measure that. Hey, look at that. Yeah, almost exactly. Let's zoom in a little. I want to make sure we're measuring that right. Cursor. Cursor should be on channel 2. Yeah, look at that. And I'd say we're within margin of error. We should see 800 millivolts if everything's perfect. We are seeing 820. That is 2.5% error. Considering that we're going through about 1% resistors, I think 2% error is pretty good. So that's good. So now if I turn on the complementary waveform, now we should be seeing twice the amplitude on the output. So now we should be seeing 1.6 volts as our peak voltage, because now I've got a positive 800 millivolts and a negative 800 millivolts being subtracted from one another. This is effectively an instrumentation amplifier right now. So we've got truly differential input being measured as the subtraction of one another, but also rectified while we do it. And let's verify. Hey, look at that. 1.6 volts on the head. Hey, that's working pretty well. Considering that we're establishing 5 kV isolation from input to output, that looks good. I have absolutely no issues with that. I think hook that up to our ADC and call it a day, because we are ready to rock and roll. What do you guys think? You guys like that? Yeah? Thumbs up? Let me know if you like that. I think that's pretty sweet. Let's feed it a different waveform, because why not? So never seen a sine wave subtracted from a triangle wave. There's a proper triangle. Oh, now I'm just having fun. That's cool. Yeah. Small signal analog. Like, there's just something about it that gets me excited. Oh. Yeah, I don't know. Square wave? That's a square wave subtracted from a triangle wave. Because why not? Yeah, cool. Alright, I'll quit playing around. Yeah, so analog discovery, 10 out of 10. I think it's like 150, 200 bucks. That's the real thing. That's the thing I didn't say. They give a student discount that makes this thing $100 delivered. $100 delivered for a basic oscilloscope, a basic wave gen, and a logic analyzer with a protocol analyzer. Like, you are not going to be able to have that much capability. So I was working on stuff in my dorm room in college that otherwise I would have had to walk to the lab at like 10 at night. Who wants to do that? Nobody. So, I mean, even if it was $300 as a student, if I couldn't have a proper lab with a scope and a signal generator and everything else, and I still don't have a signal generator because this is good enough for what I'm doing, man, you can't beat the value. Cool. So that is the analog measurement. What else do I want to see? Well, we've got this cool input here. We've got this net that I added so I could look at the output of these two, the two op amps that are effectively doing the rectification. Basically, one's measuring line greater than neutral, and the other one's measuring neutral greater than line, and then they're diode ORed, with the pull down being the input stage of this next amplifier. So I want to look at how that in plus is looking. I want to make sure that looks decent. Yeah. And maybe what I'll do is let's push the frequency. Hey. Oh, that is fun. Hey, you guys a fan of modulation? Because there's some modulation. I've got one of them set to 500 hertz and the other one to 50. Anyways. Whoa! That is some serious attenuation. Yeah, I made this thing to operate at lower frequencies, but I didn't think it would be that bad. So we should be up here at a volt. I might need to tweak this. Alright, so 200 hertz. That's probably enough. Actually, that might be good. That'll be like noise rejection. That'll be like an auto filter. That is bizarre. How is our peak detector getting the voltage across, but not the analog? Hmm. 100 hertz? Did I really design this thing to function that close to the edge? If I pull this back down to 50 hertz, is it just gonna like snap into functioning? Whoa, what happened? Did like ground come off or something? Oh, yep, I think our ground clip came off. What in the world? Looks at measurement setup. We're feeding it 500 millivolts. Okay. Stop. So just turned off the signal generators. Oh, okay. I don't know, I must have done something weird with the scope because I turned off the signal generators, turned it back on, and now it looks fine. Let's try 200 hertz. Hey! Looks great. Alright, not sure what that was. But our cursor, are we still up at? We should be up at 1 volt. Okay, so yeah, looks like our level is perfect. Oh, wrong knob. Remember that time I said the user interface was a little different? It looks like our minimum's, yeah, right around that 260. Right, let's bump up the frequency again. Let's see if we can get up to a kilohertz. I'm going to stop all channels, re-enable. Alright, looks like 1 kilohertz is a no-go. Yeah, that seems about right. So we lose... that's close enough. That's pretty much at 1 volt. Ooh, sorry, that was probably pretty loud. Bump my elbow. Okay. Yeah, so if we can get 500 hertz through without attenuation, that seems about right. And then after that, the fall off is pretty hard. It's like 2 kilohertz here. If I measure that, we are basically down to nothing, which is good, because if there's high frequency noise, we don't really want that to be messing with our control loop. So we'll do a little bit of digital filtering, we'll do a little bit of analog filtering. So the fact we're down to, that's probably 3 dB, right? No, that's half power. So we are at 40% of the output amplitude at 2 kilohertz. That's a significant amount of attenuation. All right. Oh, right. I wanted to look at the intermediate combo. Yeah. Want to look at how those 2 channels are looking. Seeing an interesting little glitch here. With that, like, power cycling of the input. Hopefully that doesn't bite us down the road. Tweaking a couple of resistors. Sorry about that. Tweaking a couple of resistors, we will be able to bond this onto like our old prototype UPS. Like we could just hook it straight up to mains, basically, and measure the output, make sure that we're getting a solid waveform. Not today. Don't have the lab set up to be safe and do that. I need to get the high voltage rated resistors. But wanted to take a moment here to inspect this intermediate node that's labeled in plus in the schematic. By the way, that is linked in the description if you want to keep up or take a look at what we are working on. I made a point to make sure. Someone had requested that last week. So, yeah. Interesting, there's a lot more noise on the high voltage side, but it just doesn't make it across. So it looks like, I mean, that looks pretty sweet. So basically what we're getting is that rectified, you know what, I bet I can probe this and show you. Bet I can probe the output of this and show you. Yes. I need to trigger on the other scope channel. Wow, this is noisy. Alright. So what you can see is this op amp is outputting, you know, it's pretty much rail to rail. Ooh. Our output one isn't rail to rail, that's where that's coming from. So maybe there's a way, if we add a DC offset to the signal, maybe there's a way we could get this to be more accurate, because that is quite low. Okay, but yeah, so this is the one, and the other waveform is exactly the opposite, so we're getting the other half wave. So that's what we have configured. Those two get diode OR'd, and that's what becomes this waveform in the middle. Yes. Quite good. Quite good. I think we're almost done. Do we need this anymore? We do not need the analog discovery anymore. So we can turn this guy off. Excellent. We've only got one more thing to test, and that is our current sensor. This is one where I didn't plan for any filtering, but I think we might want to. It's using these massive lugs because of the 40 amp rating. Oh, we're gonna add a giant ground loop because I've got to get this over to a ground clip. There we go. Menu, channel 2. So this one's going to be tricky because I don't have a big AC power source. It's really a shame. I'd love to. I just don't have one here. Is that going to be in the way? Yes. Yes, it is. Our cable's a little in the way. There we go. So what I'm going to do is I'm going to switch over to our secondary DC input. Love that diode ore. I'm going to unplug our DC power supply. Now what I can do is we're going to take a couple alligator leads. We're going to hook this right up to the DC load. I'm going to turn the voltage down to, I don't know, a volt or so. And we're going to turn the current limit all the way down. So now what I can do is I can connect the power to these lugs in such a way that when we turn on the power supply, we should be increasing the output voltage. Looking at the datasheet for this part, this is the Allegro current sense IC. Yeah. Looking at this, basically when we feed current from positive to negative, it'll increase the output voltage by what is it? I think it's like 100 millivolts per amp, 0.1 volts per amp. In this one, 100 millivolts per amp. Yep. So looking at the DC level, since we're going to be feeding it DC, ground, and I'm going to look at channel 2. We're going to AC couple this. We're going to have the oscilloscope looking at noise, and we're going to have the multimeter looking at the DC level. Alright, there we go. Hopefully you guys can see that alright. And pull the scope up a little bit. Make sure we're triggering correctly. Yes, yes. This could be another one of those where maybe we should filter the output quite heavily. I think that might serve us pretty well. Add that same, like the 1K1 mic or the 5.1K. I'm quite tempted to do that. I think maybe we should. Just gotta make sure that I'm not going to be, specifically for this one, we gotta be a little careful because we don't want to affect the accuracy of the sine wave we want to measure. So right now we're measuring 2.5 volts, and I'm just going to crank this thing up to 5 amps. There we go. So now we're at 5 amps DC, and we're at 3 volts. So, yup. This one's a pretty simple test. We're basically just verifying that the chip does what it says it should. Here, let me add in a current meter here. Get one of these cheapo meters. Set to amps. down a little bit. Alright, get that turned back on. Cool. So yeah, we're getting 5 amps out. $500 millivolts. Just crank it up as high as we can. 6.18. Looks perfect. Alright, let's tweak the clips around the other way. I'm basically just going to flip the positive and negative terminal. And we're going to turn it on. So the ripple, definitely always a factor. Got 6 amps again, but now we're down at 1.9. If I pair this back to 5 amps, we see it's almost exactly 2 volts, so this is operating exactly as it should. Not much more to it than that. Whew. Man, that's fun. That's all we have. That's all we have prepped. Like, we got through the full suite of tests. Tested out the RGB fan header. Tested out the analog reference, got that dialed in. Temp sensors, got that debugged. That was on my list since the old UPS. I think we are in pretty good shape. I'm feeling pretty good about all this. As was made evident by one of our supplies randomly blowing itself to pieces. Not a huge fan of the NCP3020, but next week we should have everything that we need to continue on this journey. Oh my goodness, there's comments that weren't scrolling. Anyways, yeah, I think we'll be in pretty good shape. So the next couple weeks, we're gonna dive back in. Let me know what you guys would rather do. I think there's gonna be a lot of work. Oh, no problem, JD. Glad you enjoyed. Thanks, NoCorp. I'm glad you enjoyed too. So we're gonna have the new bucks. So I'm not sure what you guys would rather do. I was planning on like getting them dialed in and working, so we don't have to keep talking about buck converters all the time. I have a feeling the bring up on the new converters will be quite simple. We're just going to get them kind of wired in here for 5, 15, and 12. Do some efficiency, line load, right? All that stuff. Fills in current. Yes. Yeah. Yep. So to give you a little bit, phase delay is a huge issue for control loops. And yep, that's definitely something that I need to keep in mind, right? That's why there was no filter on this originally. Right now, the way that we're implementing that feature is we're actually looking at whole main cycles. So what the control loop does is it measures one full cycle, one full AC cycle worth of data, and then it averages it and calculates the RMS. And then it regulates RMS output power. Yep, current measurement. Yep, maybe I said the wrong word. I meant to say measurement. So what happens when I do that is I make phase delay irrelevant. Since we're doing it on a cycle-by-cycle basis, it doesn't matter if we start at 0 volts or full peak voltage, because I know that wherever we start, we're going to come all the way back around that main cycle and we're going to capture one full cycle worth of data. So our RMS measurement will always work out. So if that's how we continue to do it, then there won't really be an issue with adding phase delay if it reduces noise. But we're already doing averaging in the ADC. It's probably okay. The thing that we're really regulating is output voltage. And then we're monitoring output current to calculate power. It's not necessarily required. It's not really a factor in the control loop. The control loop doesn't really consider current unless it trips the overcurrent limit, in which case, of course, it does a soft start. Yeah. So phase delay is very important, especially in the voltage feedback loop. it's still kind of important to have it in the current, because then we know that we're getting peak power at about the same time. I don't know. It's just something to think about. Something that I'm going to be thinking about as we move forward. But I certainly think that what we have right now is workable. As long as I tweak those couple component values on the analog references, man, we will be good to go. I'm pretty excited. So yeah, let me know if you guys are interested in hearing more about the Bucks. If you want to spend some time next week doing line load short circuit fault testing, because I'm doing short circuit fault testing and I do not want those regulators to explode. I want to be able to do whatever I need to those and have it just be okay. So let me know if you want to spend some time talking about the Bucks next week. Otherwise, I think what I'll want to do is pick up where we left off. We want to do the battery charger. So that'll be a constant current, constant voltage, fun analog circuit. But maybe we can do a little bit of both next week. Might be able to do a little bit of both. Then after that, all we've got left is the backups. This will be battery voltage backfeeding the 24 volt rail. So it ends up being a third ideal diode that provides 24 volts to the low voltage circuitry when mains has failed. And perhaps what we'll do is we'll drive this analog measurement circuit with the isolated flyback, backfeed 5 and 15 volts in here, and make sure that this whole signal chain still works great when we isolate it. So that's kind of the plan with the proto. Once we're done with that, it's time to finish polishing the design and start ordering some proper boards. Whew. Weird. New schematic then? Yes. Yes. So basically what I made is just a little, it's basically just this section of the design. It's just one of these converters. We'll have 3 little dev boards. And I happened to order 20 and some extra parts. Yes. No corp, that is correct. The reason why I went with the diode rectified high side NFET integrated is because it makes the lossless current sensing work without needing to pair your controller with an NFET. It just kind of does it all, which is super great. And the reason why I ended up going for that is because it has a what was it? Words are hard. What was it? I don't know. I'll come back to it. I lost my train of thought. I just want to take a moment to let you guys know about the next stream we'll be doing. It will be next week, same time, same place. You know where to find it. So 8:30 Central Time next week. Words are hard. Thinking is harder. Agreed. But thanks for watching, guys. We'll definitely run through the Buck more next week. We've got a video coming out soon talking about designing the new board and some of the trade-offs that we went through. There were a couple controllers that we looked at, but I remember the efficiency. The efficiency of the diode rectified Buck is going to end up being like 85-90% efficient. And I looked at what we were doing, and I was going to be okay with this design if it could output 3 amps and it was at like 80% efficiency. So I'm like, if we really don't need the efficiency of a synchronous rectified controller, why are we adding the cost and complexity and all these extra parts if we literally don't need it? Just use the simpler topology and move on. So that's what was the final that was the final point where I realized, yep, this architecture doesn't really make sense. I was just doing synchronous rectification because I prefer it, right? I like high efficiency converters, but I'm just not sure that it's needed for this. So I don't know. It'll be fun regardless. It'll be fun. Yeah. That's about all I have. So we'll see you next week, guys. Hope you learned something. Hope you had some fun. We'll see you again soon. Bye. Actually, one more thing. Sticker giveaway closes in like 2 weeks. If you want a sticker, do it. They're great. EEforEveryone stickers. Check them out. Thanks for being part of this awesome community. See you guys soon.